5, 4, 3, 2, 1, 0. All engine running. Liftoff.
Hey everyone, welcome to another episode of the Space Business Podcast, where we investigate all the exciting ways in which people participate in the new space economy, by conversations with entrepreneurs, executives, investors, and other members of the space family. I'm Raphael, Roettgen, and I'm an investor in and advisor to space companies. Just as a reminder, this podcast is for informational purposes only, and nothing should be taken as investment advice. Sadly, I am not a rocket scientist, but I am an alumnus of the International Space University, which is also our partner in the podcast. Here's a short message from them.
The International Space University, founded in 1987 in Massachusetts, USA, and now headquartered in Strasbourg, France, is the world's premier international space education institution. It is supported by major space agencies and aerospace organizations. ISU offers the Master of Science in Space Studies program at its central campus in Strasbourg. ISU also conducts the highly acclaimed 2-month Space Studies program at different host institutions in locations spanning the globe, and more recently implemented the Executive Space Course, the Southern Hemisphere Space Studies program, and Commercial Space program. ISU programs are delivered by over 100 ISU faculty members in concert with invited industry and agency experts from institutions around the world. Since its founding, 33 years ago, more than 4,800 students and participants from over 100 countries graduated from ISU. Follow us on social media at ISUNet.
Our guest on this episode is Daniel Faber, the CEO and founder of Orbit Fab, a California-based startup that is developing infrastructure to refuel satellites and other spacecraft in space, or as Daniel calls it, gas stations in space. He will describe how that all works in detail during the episode. However, Daniel has a much longer history in the space industry, which includes being CEO of the former asteroid mining startup Deep Space Industries. He truly is passionate about building up a functioning economy in space and has a very holistic view about it. The second half of the podcast is all about this, so make sure you listen to the entire episode this time. In this vein, please enjoy my conversation with Daniel. So, hey, we are here today with Daniel Faber from Orbit Fab. How are you doing, Daniel?
Yeah, really good. Thanks, Raphael. Great to be here.
Good. Great to have you. As coronavirus is still continuing, this is yet another remote podcast, but the last few have worked fine. So I think this one will be okay again. So as always, Daniel, if you could start, please, with an elevator pitch of Orbit Fab.
Yeah, sure. Orbit Fab is building gas stations in space. Our goal is to provide mobility to satellites that currently, when you launch them, they move as little as possible. They have a fixed amount of fuel. And so we're trying to solve that problem by building a propellant supply chain and all of the technologies that are needed so that those satellites can get access to that propellant, allowing them to have unprecedented business model flexibility, to extend the lives of their valuable assets in orbit, and be able to do missions and provide services that haven't previously been possible. So we've 2 years ago we founded. We've already built hardware and launched our tanker test beds to the International Space Station. We actually became the first private company to resupply the space station with water. We've also built a fueling port, allowing satellites to be refueled in orbit. We have a number of commercial customers and government customers in the US. So that product is doing well. And now we're working on rendezvous and docking interfaces and our first generation of tankers. We expect to have our first operational tanker in orbit in about a year.
Great. So it's a tanker, basically. When you said gas station, I was sort of very excitedly imagining sort of like a regular gas station with an attached convenience store and all of that. But it's essentially a tanker. Could you maybe help us to visualize that a little bit more? Sort of like, what kind of size are we talking about here? What will the tanker look like? Is that like a big metal structure or some other material? And then also, how does that big thing get up to space?
Yeah, sure. So our tankers vary in size. Our first generation of tankers are going to be quite small so that we can start the operation cost effectively and prove that everything works. So they may be only a couple of feet long and about a foot wide, holding something like 10 or 15 liters of propellant. Very modest, but it lets us test all the systems. Our largest tankers that we're planning are multiple tons, and so there's much more capacity there. We get these tankers to orbit on rockets, so we fill them on the ground and put them on the rockets. But we can use any rocket, and because we're managing the supply chain and the logistics, we can go for the best deals on the rockets. And then sort of bring that propellant together in orbit and take it to where our customers need it. Our tankers really do operate like gas stations. We put them in convenient locations, and then our customers come to us. We don't carry all of the docking equipment and everything needed to go to the customers. We rely on tow trucks, if you like, on satellite servicing vehicles, and there's a lot of companies now that are working on those types of vehicles. So we work with them to be able to deliver services to the constellations of satellites that are doing telecommunications and remote sensing and other types of things.
Understood. Let's unpack that a little bit more because you made me curious. So coming back to my question, so still a tanker, I suppose, is probably a big hollow structure. So that's not a very efficient use, I suppose, of valuable space in a rocket. Is there some sort of like clever way to mitigate that? Like, could you like fold it up or partially construct it in orbit?
Yeah, for us, we have to get the propellant off the ground. So we need to make efficient use of the fairing space on the rockets. And that means we make our tankers the size and shape that's needed to get propellant up. Our customers, however, they have much more strict requirements on the time that they get to orbit. They need to get into operations to serve their customers quickly. They need to pay high premium prices on rockets so that they have very reliable service to exactly where they need. It's much better for them if they're lighter, if they don't have all the fuel in them up front. So you don't want to pay for 15 years worth of fuel that your business model may change in 5 years. So by offering propellant in orbit, we can solve that problem for them, and they can launch sometimes with no fuel at all and then gather fuel on orbit. But then our customers don't want to launch with no fuel and just a big empty fuel tank. That takes a lot of that the space on the rocket, that valuable rocket fairing volume. So we've also invented an inflatable tank, a tank that you can take up stowed and then pump fuel into it, and it will inflate. So that's one of the pieces of the future technology. That our own tankers, because they have to launch on the rocket, they've got to survive all the vibrations and everything else, and they've got to have all the fuel inside them. They're actually rigid tankers, just big tanks of fuel.
What kind of materials would you be made of? Is this metal?
We are expecting to start with metal. We've been looking at composite tanks. Of course, every kilogram that we can save on the mass of the tank is an extra kilogram we can have as fuel to sell. And so we're very acutely aware of the economics of that. At the same time, we trade that off against the economics of having to pay upfront for an expensive tank when a cheap steel tank might be great but heavy. So there's a lot of trade-offs there. Our first tanks will be metal, and our later tanks, as we get to the larger tanks, and we're able to realize those cost savings effectively by switching to composite tanks, we will.
And I suppose your main customers would be obviously operators of satellites. And at least for the moment, does that mean that your main fuels would be the noble gases like xenon and krypton? Or are you already looking at other fuels?
So we get most requests for hydrazine, which is a chemical propellant, and as well as xenon, which you mentioned, which is used for electric propulsion systems. Even though they're electric, you still need to have a propellant to push against. So those are the most common ones. There's a few others as well, and so that's where we start. Longer term, there's interest in cryogenic propellants, liquid hydrogen and liquid oxygen, for example. That's a much more difficult technology. It takes a lot more money to build that sort of infrastructure out. So that for us is not our first generation, but it's something that we will get to in the future. Yeah, those are the main sort of propellants that we look at, and that's from the satellite customers, the operational telecommunications and Earth imaging and other types of satellites, but mostly looking at the what I've called tow trucks in space, satellite servicing vehicles that actually do repairs or life extension or inspection or towing of satellites between different orbits. These types of tow trucks, and there's 34 companies building these tow trucks. One of them, Northrop Grumman, is currently commercially operational in geostationary orbit. These tow trucks use a lot of fuel because they do a lot of moving around. And so they're our early customers, is just to provide the fuel across all of the tow trucks in orbit.
So that's a good point. You mentioned Northrop Grumman. So if I'm not mistaken, that happened just a few weeks ago when Northrop Grumman's mission extension vehicle successfully refueled an Intelsat communication satellite in geostationary orbit. I believe that's the first time something like that had ever been done.
That's correct, yeah. And it was really good to see that. They've really proved that is a viable thing to do. And there have been a couple of press releases come out from their potential customers saying that they're interested, they're talking, they're signing contracts and that kind of thing. So it appears that there was a lot of demand from the constellation operators that is now appearing now that service is commercial. And that's going to help the other satellite servicing operators build their businesses out as well.
And as you mentioned, I suppose anybody who's operating what we call a space tug, so people like Northrop Grumman or people like Momentous, to mention a startup company as well, they of course need fuel themselves, which I suppose then again you guys are well placed to provide. And I assume, given that these tug services need higher thrust, that's probably where the hydrazine and the other chemical fuels come in.
That's exactly right. So for some of their operations, they need high thrust, and the fuel efficiency matters a bit less. For other operations moving between the orbits, they want fuel efficiency because that can take a lot of fuel. And so some of them actually have both the electric propulsion and the chemical propulsion on board, which makes the supply chain hassles a little bit more difficult. But if you go to a gas station, you get your premium and you're not quite so premium and your low grade gas. So it's a similar kind of thing. A small number of propellants is quite manageable.
And so I guess your initial types of customers would be these operators like an Intelsat, like an SES, for example.
So actually, our first customers are the tow trucks, who then service the Intelsats and SES. So yeah, we work quite closely with those. Northrop Grumman actually on stage at Satellite 2020 a couple of months ago stated publicly that they intend to purchase propellant from Orbit Fab. So already making a lot of progress in that direction.
Did you have any interest from the government as well?
Yes, quite a lot. We have some contracts with the US government, and they've been looking at the fueling ports. They've been looking at the technology for docking. They've been looking at, for example, transferring xenon in orbit. Xenon is stored as a supercritical fluid, which makes it an interesting thermodynamics challenge and fluid flow challenge to be able to move it between tanks and keep it pressurized. So there's a lot of sort of important technology under the hood that the government has shown an interest in having access to, and as they sort of want to build out their own capabilities.
But there's also obviously a lot of talk starting about cislunar transportation. Is that something where you think ultimately you guys will also help?
Oh yes, you need a lot of fuel to get to the moon, and we've done the math a number of different ways as to how that might happen, how we might be able to help that. What really excites us there is the potential long term that we could extract propellants from the moon, which could then be used in space for getting off the moon and for getting back to Earth, and then even for putting into our tankers in Earth orbit and supplying to people going back out to the moon. So long term, there's a really interesting, again, propellant supply chain coming down the gravity well instead of up.
This is a really interesting point. So it sounds like you guys have probably run the calculation, which I'm going to ask you about now, because as you mentioned, obviously Earth is sort of a very deep gravity well as the solar system go, and the moon has only 1/6 of Earth's gravity. So could it actually ultimately be cheaper to bring propellant from the moon to Earth orbit rather than bringing it up from the Earth's surface?
I think it will inevitably be cheaper, especially if you consider using propellant or any other sort of consumables on the surface of the moon, because to get down to the surface, you have to fly your way all the way down. You can't throw a parachute to get to the surface of the moon. And so you burn fuel, not just get to Earth or to moon orbit, but all the way down. If you can make that fuel on the lunar surface, that's much easier. And once you build that infrastructure, like you say, getting it from moon surface to moon orbit and into Earth orbit, very much less propulsive capability that you need. You burn less of that fuel. I'm also, in my background, when I was running Deep Space Industries, our big, hairy, audacious goal was asteroid mining. And we looked at how we would build the supply chain from asteroids back into Earth orbit. And specifically, we were looking to extract propellant from the asteroids, not metals. The economics for that don't work very well. The economics for returning fuel and propellant from asteroids works very well. So there's a question as to whether the first celestial body that will be mined will be the moon or the asteroids. Undoubtedly, though, it will be mined for propellant and for fuel. So we're very bullish on that long term.
And you mentioned DSI, and we shall definitely come back and talk about that. Now, when do you think this is actually all going to happen? When do you guys expect to have the first of those tankers in space?
Yeah, we expect to have our first operational tanker in orbit in about a year. We've been working steadily towards that. We had 2 tanker test beds inside the International Space Station, like I mentioned, about a year ago. And we did all of our propellant transfer tests. We tested the feed systems, the tanks, the plumbing. We did some tests on technologies for the docking. We've since completed our docking and fueling port development. So those items are coming along. So all the pieces are coming together to be able to fly and operate that first commercial tanker in about a year.
So you have already a launch booked? That sounds like it's very near term.
Because of the way that we look at launches and the deals that we want to do with sort of long-term agreements with launch companies, we have quite a number of launch companies that have launch slots that we could take up. So we haven't felt a need to identify a particular launch. But needless to say, there is enough opportunity these days that we can fly as soon as we are ready.
Understood. And then those tankers, what sort of orbit would they stay in? Because I suppose you could serve both geo customers, but as well customers in other Earth orbits, and so that's a very large distance in between. Where I know the space ducks come in for that transport, but still, what is your thinking as to where you will station the tankers?
Yeah, the operational satellites are in geostationary orbit or in low Earth orbit in a number of different inclinations. So we will have tankers in 4 different inclinations in low Earth orbit and in geostationary orbit, which is only at the equatorial inclination.
Okay, in the low Earth orbit scenario, roughly how high up are you guys thinking? How many kilometers?
So once you're in the right inclination, it takes less fuel to change altitude than it does to change inclination. So we'll put our tankers at an altitude at which they won't get in anyone's way. They're not a hassle, and they're accessible. So it'll probably be somewhere around 500 kilometers. But there's some different parameters that we look at depending on the customers that we're serving and where we get dropped off when we get to orbit.
Is there any specific considerations people need to have talking about tankers with regard to dangers from space debris? I mean, are any of these fuels sort of like self-igniting in the worst case scenario?
Hydrazine is a monopropellant, meaning that it burns with itself. And the xenon is a supercritical fluid, so it's stored under considerable pressure. So we have to be careful about that. We're building in to our systems a degree of micrometeoroid tolerance, so impact tolerance, but also by having it at an altitude like 500 kilometers or so, if there are any issues, any debris would re-enter the Earth's atmosphere and burn up. So effectively, it'll go away after just a couple of years. And that's one of the considerations with altitude. But also, we do realize that on average, 1% of all spacecraft die every year. That's the average failure rate from the radiation environment, from things going wrong. So while we would like to believe we will build very robust and reliable tankers, even the most robust and reliable systems fail about 1% per year. So one of the things we look at with our customers, these satellites servicing effectively these tow truck in space companies, is that we will have contracts with them to be able to remove any of our tankers that fail. And so in that way, we'll make sure that we don't create debris by just unintentionally leaving our tankers in locations they shouldn't be. So we're quite mindful of that and design our systems with several aspects in mind to make sure that we are keeping space clean and useful for future applications.
Cool. And since we're a business podcast, I want to briefly touch on the economics and the sort of the quantitative benefits for the satellite customers. I suppose what you're doing at the end of the day is giving people an option of extending the life of the satellite. So depending on what type of satellite we're talking about, like I suppose if it's lower Earth orbit, well, again, it will really depend on what exactly the type of the satellite is. But maybe including the launch, let's say a satellite costs something like $2 million. And then a lot of the satellites at the moment, I guess, have lifetimes projected at around about 5 years. So if you depreciate it over 5 years, it's about a $400,000 cost per satellite. And then I suppose it's comparing that amount with the amount they would pay for refilling the tank. Is that the correct way of thinking about it?
That's right. I'll give it to you in a different analogy. Because our first customers are the tow trucks, and we intend to be selling fuel to these tow trucks, the satellite servicing vehicles, for their own use initially. The analogy there is it's like buying a new tow truck to go into this tow truck service and then towing 3 cars, running out of fuel in the tow truck, throwing your tow truck away, and buying a new tow truck. That is how the business models operate right now for satellite servicing. Now, if there's a gas station and you can refill your tow truck, you can now use that asset, which are very expensive assets. They're not cheap to build and launch. You can now reuse that asset not just 3 times, but 10 times or 100 times. So now finally your asset utilization is considerable. You can amortize your initial CapEx cost over a lot more operations, but also you aren't doing it by increasing CapEx cost. You're doing it by increasing OpEx, which gives you real flexibility. And so this way we can really make those business models work for satellite servicing operators, meaning they can then provide cost-effective services to their customers, which will make then space just a lot more busy place, a lot more flexibility all around. And that can help close business models that just haven't been viable before. When we look at the operational constellations, in geostationary orbit, they're multiple-ton spacecraft that still dominate the market. They have hundreds of kilograms of propellant. They use about 50 kilos of propellant a year. And each year they're generating, the new satellites, hundreds of millions of dollars. The older satellites, even at the end of their lifetime, they're generating tens of millions of dollars per year. And they're retiring these satellites just because they ran out of fuel. So they've taken up all of this CapEx initially to get to orbit so that they can have very long lifetimes of fuel. If the market's changed, they're left with an expensive asset that they've sunk the cost on. If the market gets better and they want to extend it, they're stuck with no option to do that. And so that's what we see with how Northrop is capturing that market with their mission extension vehicle. So all of that plays into just providing that flexibility. And then the last part is the mobility part. What is the value of being able to move a spacecraft around when at the moment all the satellite operations, the primary thing that they're trying to optimize for is to reduce the use of fuel. Every time you have to move a satellite to a new orbit, to a new configuration to serve a new customer, you use up fuel and you reduce its effective lifetime, which reduces its revenue generating capability. So there's a huge value just to being able to take that out of the equation, to know that there's an operational cost to the move, but it doesn't take your capability away. And you can do a much easier calculation and to see how much profit you can generate and what more you can get out of that asset that you've already paid hundreds of millions of dollars for.
That makes a lot of sense. And I want to come back one final time on sort of the comparison to gas stations on Earth. So I understand that won't be the convenience store for the foreseeable future, but very often we have also sort of like car repair shops jointly with gas stations. Do you think ultimately there will be something like where at the places where you store the gas, you might store other spare parts for satellites as well that then the space tax could take along, like, I don't know, like spare solar panels or something like that?
Yeah, absolutely. We get asked for that quite often. And I think that modular components and replaceable components for repairing satellites is definitely something that is coming. We're not actively working on that part, but I can see where our gas stations effectively become small warehouses too, where we can hold those components for the servicing vehicles while they go off and do different missions. So we've thought about that. We've thought about various other things. One day I'd love to sell donuts at every gas station. But we're at the moment hyper-focused on nailing our core business, and that is the propellant supply chain. It's about the extended mobility, the access to that propellant from our customers. That's the problem we're solving now. We'll get to those other problems in due time.
I'm going to remind you about the donuts in 20 years' time. I mean,
hey, with Tom Cruise shooting a movie in space, you think his crew won't want donuts?
Yeah, and plus, if you achieve that, I was going to say Tom Cruise is an excellent point. I was going to say that ultimately, then I suppose you will have the Space Force or the Space Police Force stopping by the gas station picking up the donuts as well.
You got it. All patrol cars are going to want to be supplied with donuts.
Yes, and then we shall have a a convincing, like full, complete space economy, which is actually kind of what I want to talk about now in the second half of the podcast. Usually we talk only about the companies, but I know that your background and your sort of like passion for the space business in general is much more holistic. And you've already mentioned your history of DSI, so one of the two prominent asteroid mining companies, the other one being Planetary Resources. Mm-hmm. Can you just give us a few minutes sort of like how your sort of voyage into space started, like how you got to DSI, what fascinated you, and like how you think about the space economy in general?
Yeah, gosh, how far back would you like me to go? In first year university, I decided that I wanted to do something interesting with my life and something that would help humanity. I decided that we should get people off this rock. That would be, thinking about existential risks, and I've always had the problem of not being able to think small. Considering existential risks to humanity, getting people off Earth seems to be the most important thing that we could do. And so I decided I would work on that problem. So I made a list of all the companies or all the industries that I thought might be able to justify the cost of creating the first permanent job in orbit. And that list consisted of tourism and asteroid mining. And I couldn't see tourism working, or rather, I couldn't see myself being a tour operator. I could definitely see tourism working. I couldn't see myself as a tour operator, so I decided that I'd have a go at asteroid mining and set about trying to understand the technologies and the business models to make that work. So I worked on the core team of building about a dozen satellites. I then started building companies. The first one was instrumentation for the mining industry. Second one was high-speed internet for Antarctica. We built the first Ka-band transponder for a CubeSat-sized satellite, a very small, very high bandwidth radio that would have excellent implications for deep space and asteroid mining work, but also had great commercial application in low Earth orbit. Then Deep Space Industries was the third startup that I ran. I joined that full-time about 18 months after it was founded, and the first business model there was looking for billionaires, trying to find a billionaire that would like to fund it. And really, that had been proved that it wasn't going to work when I joined. But we got a small amount of investment to be able to build the engineering team. And the strategy that I bought in was to build the technologies that we would then need and be able to use, not only to go out and mine asteroids, but also that we could sell to. So we wanted to build the thrusters that could run off the propellants that we could get out of an asteroid, because those didn't exist yet. So we started very modestly. We built a flying steam kettle. We built a small thruster that ran on water that was very, very low cost, solved a problem. There was a gap in the market. Wasn't the greatest fuel efficiency, but was something that was very simple, allowed us to get into the market, make some sales, build a reputation, and build a whole product line around the thrusters that could be used for small satellites and progressively larger satellites, and could be one day refueled from asteroid-derived propellants. At the same time, we started to look at different subsystems we could build, power subsystems and the like, and whether we could do entire satellites, considering that once we're bringing fuel back from asteroids, we didn't want to be disrupting our customers. And if our customers were satellite integrators, we thought hard about how to avoid disrupting them and decided the best way to do that was to be a satellite integrator and to sell to ourselves. And if we really could get a cost advantage from using asteroid-derived propellants, then we would do that. And therefore, the customers of that business would be the constellation operators who want to buy transponder time. They want to buy the lifetime of the asset on orbit. And by using the asteroid-derived propellants, we believe that we could do that more cost effectively. So in going down that path, we won the prime contract to supply Hawkeye 360 with the first 3 spacecraft in its constellation. And they, of course, were built around this thruster that we had. And we had an unfair advantage to win that in that we had the thruster ready to go, which nobody else had in the market. So we were really leveraging that hard. So we built that up to about 10 million of sales after 2.5 years. And then I left Deep Space Industries and started working on step 2 with the thrusters that exist to sell propellant. I'm now working on the propellant supply chain.
So do you still think that first feasible industry that's going to happen in space is going to be the natural resources in some way? I suppose it could be like tourism, but let's accept that you don't want to be a tour operator.
Well, actually, quite interesting. When I stepped back from deep space industries, I looked at 3 different business models because that list that I had 25 years ago had expanded a little. I still think tourism is very possible that it will create the first permanent job in Earth orbit. Asteroid mining, I'm actually less bullish on because I think that we'll go ahead and do that robotically, though that will be difficult. I think that's how that will go. But the other things that I looked at were in-space manufacturing, specifically manufacturing semiconductors in orbit where they have much lower defect densities because there's no buoyancy, there's a lot less stress on the crystals. And second was in-space entertainment content. My big, hairy, audacious goal to that business model was to organize the first Olympic-scale sporting event, which I figured would take us 20 or 30 years to get to. But that was the goal, and then we built out a path of different entertainment products that we could be producing in space. And that's when I saw the Tom Cruise thing a couple of weeks ago, it was exactly the types of things that we were thinking of. And so, yeah, I'm rather bullish on both of those, in-space content as well as tourism and as well as manufacturing.
And the manufacturing part is, I suppose, also starting to happen. I mean, you got those companies like Made in Space, which are investigating manufacturing quite a few different things like fiber optics and so forth. Now,
yeah, the one that excites me a lot there, I heard pancreatic islet cells are difficult to grow, but they will grow in space. You can actually grow an artificial pancreas. So you could send up your stem cells in a box, and they can grow them into an artificial pancreas, which you can then implant, and you're implanting your own cells, so you'll never reject it. I thought that was a fascinating one, and apparently can't be done in 1G. So there's a whole bunch of medical type manufacturing things as well that might be really fascinating, as well as the material science type things.
Yeah, I got to thank you, Daniel. You're actually reminding me of all of the different guests I was planning to invite on future episodes of the podcast. Definitely want to have the Made in Space guys over, but you're right. I need to have somebody from the life sciences field over again, because you're absolutely right. I mean, basically the effect is that in microgravity, you can just grow cells in a 3-dimensional way. So, for example, if you grow a cluster of cell that ultimately could be organ tissue, even, you don't need scaffolding, which you do need on Earth. Yeah. But that's a different podcast episode. So
I'll be looking forward to that one. Yeah.
Me too. Hey, did you ever think about energy generation in space, or do you think that's too early on?
I did actually. The list that I initially had 25 years ago was tourism, mining, and space-based solar power. The problem was I could do math, and I quickly realized that just wasn't going to work. The cost of lifting material off Earth is prohibitive. And short of a 2 orders of magnitude reduction in launch cost, the only way to make that work is to mine asteroids first and get the material from there. So with SpaceX, we may get to that 1 order of magnitude cost reduction. I'd be surprised if we got to 2 orders of magnitude, but we're inching in that direction. I'm still bullish on asteroid mining being the key enabler for space-based solar power.
That calculation was 20 years ago, right? I mean, you have actually effects on various parts of the calculation, right? You have, like you said, the launch costs, and then if you go from something like $10,000, which it was not very long ago, right, to possibly a few $100s, you're almost at 2 magnitudes on something like a Starship, if that eventually works. But of course, the efficiency of solar cells has also improved dramatically in the meantime. So maybe we should run that calculation again.
I absolutely agree. And in fact, John Menkins, who is one of the leaders in the field, runs that calculation about every 5 years or so. He put out the latest calculations, another book, the latest engineering concepts. And yeah, he's getting close. Like it's definitely getting closer. If Starship worked with the prices that Elon Musk has been saying he can get to, then yeah, we'd be there. It'd be great. But I think that those numbers require amortization across perhaps 1 million launches. And I don't know how feasible it was. If there's one thing we learned from the space shuttle program, never rely on numbers that need to amortize across 1 million launches. The world's cheapest launch vehicle was supposed to be the space shuttle, and it ended up being the world's most expensive launch vehicle. So the jury is still out on what's going to happen with that.
This is an excellent example for our listeners who may not everybody may be familiar with space shuttle history, but I think the original estimate or target for a shuttle launch in the early 70s was $5 million per launch. So even if you
per pound.
Yeah, so even if you adjust that for inflation, I mean, you're sort of like getting to where the Starship wants to get to. And obviously, in the end, every shuttle launch costs like $400 or $500 million. But let's get back to asteroid mining, since you know it very, very well. And it's obviously a fascinating sort of field to dream about. In your mind, are we there? Like, what are the big remaining obstacles? Like, for example, do we know what we actually could economically mine, like what kind of materials we would go for? And the second question would be sort of, are there any remaining technological barriers?
Yeah, if somebody was mining asteroids today, I know the price that I would pay for water in Earth orbit. I know the price I'd pay for other materials in Earth orbit, right? We're trying to build that market. So I think it's propellants. We need hydrogen, carbon, and oxygen, and we can combine them into a decent range of propellants. There was some good work that was done by Deep Space Industries that was published under a NASA contract, which identified hydrogen peroxide and dimethyl ether as two very interesting propellants. And there's been some further work since on exactly what you might use. It's part of Orbit Fab's long-term ambition to become the petrochemicals company in space and be doing the processing of those types of propellants and the refining of materials. In terms of the other things that you need to stand up a new mining paradigm, there are really 5 things. One of them is market. But you also need the geological understanding, the technology to extract the material, the financing, and the regulatory environment. And each of those is a problem right now. So Orbit Fab is effectively working on the market side of this asteroid mining problem. On the geology side, we know a lot about the asteroid composition, the mineral compositions, because we have meteorites that fall from the sky, and their reflection spectra match the reflection spectra that we can see through telescopes of the asteroids, which means that those asteroids, about 60% of them, we have a spectral match. And that means that those asteroids their surface is almost homogeneous of that type of mineral that we see in these different meteorite classes. We can match them to different meteorite classes. And if the surface is homogeneous, then the whole asteroid is probably homogeneous, so we know what the minerals are in the asteroid, which is fantastic. However, the things we don't know is the rock mechanics. We don't know how hard it is. We don't know what it takes to fracture the rock, what the grain size is when it fractures, how hard those grains are, what's the variation with depth and across the surface. Is it fluffy or is it as hard as rock? Or is it worse? Is it these carbonaceous asteroids? Because of the UV environment and everything, they have actually baked into a plastic-like surface. So there's a whole bunch of things we need to ask about specifically rock mechanics. And just a note, recently there is an Institute for Rock Mechanics that has just stood up a committee to look at asteroid and lunar rock mechanics and how we can answer this question. So to me, that's a fascinating one and really important on the geology side. The other thing, when you look at the moon, we know less about the geology of the moon because we've only got grab samples from 5 places, and it's covered in regolith. It looks like a slag heap. It looks like the kind of things you would throw out after you take all the good stuff away. But then again, we haven't looked for the mineral concentration locations because most of the Earth is covered in low-grade diffuse silicate material. What we need to do on Earth is, of course, find the mineral concentrations, the ore bodies, that are then viable to extract. On the moon, we haven't had the chance to do that. There's a layer of regolith. We need to do more work. The only one that we have a really good indication of is the water deposits and the volatile deposits on the south and north pole. And so they're very interesting but need a lot more work. They're likely at very cold temperatures, possibly as low as 40 degrees Kelvin, and we don't have equipment that can dig at that temperature. So there's a lot of unknowns about how we would go about extracting something in those environments on the moon. And we don't know the rock mechanics or the geological context for that. So there's more questions about the moon's geology actually than the asteroid's geology. So that's the geology side. The technology, of course, as I mentioned, on the moon, working at 40 degrees Kelvin is difficult. And the asteroids, you're working in a very, very low gravity environment. You effectively dock to an asteroid. You don't land on it. And so we have to figure out how to stay affixed to the asteroid while we extract the material. And how to work with the different mineral and rock mechanic properties there in that environment and build high reliability equipment that is going to operate in a very difficult environment. So there's a lot of technology that needs to be worked out. The one that I find interesting also is then the political issues, the regulatory issues. So that includes just knowing what the tax rate is so that you can do the math on the business. And we don't know what the tax rate is for mining an asteroid or the moon at the moment. There's no regulations. You also need to have secure tenure over the minerals in the ground. Otherwise, you won't get financing for it. Unless you're a billionaire, in which case you can finance the whole thing yourself and take that risk. But traditional mining financing, which makes it viable for the rest of us to try and build an asteroid mining company, you go to the markets in Canada and Australia, and 60% of global mining exploration finance comes through Canada. They just have a real center of expertise up there. But you need to have a secure asset that is your tenure over the minerals while they're in the ground. And that needs to be your tradable asset. And you build value on that by looking at prospecting missions, doing analysis, proving that your theory about that mineral concentration is actually correct. And you can spend hundreds of millions of dollars or even $1 billion looking at that and proving that that works before you go ahead and spend $1 to $10 billion building a mine. But if you spend that money, then you're carrying that cost of that early financing as you go to build up your mining operation. You don't want somebody to get wind of the fact that you think you've found some viable mineral concentrations, and then jump your claim, and then just go in and take it from you. So we need to have some regulatory mechanisms that give you that protectable, tradable asset before we can go to the finance communities and ask them for the millions and tens and hundreds of millions of dollars that it's going to take to get this off the ground. And that just doesn't exist at the moment. Even the Luxembourg and US laws, they grant the right to ownership after it's extracted, but aren't yet giving any recognition of any tenure over those while they're in the ground.
Yeah, I must say, if I'm listening to you like that, and myself being a financial markets person, I'm hearing, the technology is actually not solved yet. There's quite a few challenges to still overcome. And you have regulatory uncertainty. That makes me relatively pessimistic on any sort of private financing, unless it is the sort of billionaire passion financing. But then you'd need a billionaire with quite a few billion and sort of in liquid resources. And that takes you down to a few people on the planet, which probably means then this will have to be in the beginning underwritten by governments, by state actors. Would you agree?
Yes and no. And we chip away at the problem, right? If the governments are prepared to put in place a secure tenure regime, and that I believe is what the latest initiative from the US, which is getting international support, is all about, then that takes away that risk on the regulatory side, right? We just need that certainty to be put in place. The technology side, we're working on it, right? The geology side, we see the Hayabusa mission, OSIRIS-REx. These now have gone to the right types of asteroids, the carbonaceous chondrite asteroids, the ones that are volatile rich. And the greatest thing was they showed up and immediately they saw water. And that was always the question: are these asteroids wet? And we expected actually that they were going to be dry on the surface because they're baked by the sun for billions of years. Expected them to be dry on the surface, but have the water-bearing minerals inside. That was wrong. I was wrong. Those minerals are actually on the surface. We can see the hydrated minerals at the surface of these asteroids, which is fantastic. They are wet. And so that immediately took away some of the geology risk there. The rock mechanics risk, just by a Hayabusa dropped a grenade, basically. They blew a small hole in the asteroid to try and see what was just underneath the surface. And that worked. That told us a lot about the rock mechanics. Both Hayabusa and OSIRIS-REx have done sort of bump and grab missions to grab samples, and that's told us more about the rock mechanics. The fascinating mission out to a comet by Rosetta, when they dropped the lander. Now, they ended up losing that lander. It bounced a couple of times. They got a bit of data back from it. But the fascinating thing, when they dropped it, when it hit the surface, it actually caused a little crater to open up. And they described the surface as creme brulee. It looks like it was a sort of tough, crispy surface that the lander bounced off, but then it shattered the surface, and over the next couple of minutes, that surface sank into a depression. And so it's very fluffy underneath. And this was just a fascinating insight into the mechanics of that kind of rock material on a comet. Now, some of the carbonaceous chondrites, they spectrally look very much like the comets. And so we need to find out whether those rock mechanics, that really powdery, really friable surface, is what we're likely to see on the asteroids. What we've seen so far from OSIRIS-REx and Hayabusa is that that's not the case, that the ones that are closer to Earth because the comet was a lot further away. The ones that are closer to Earth are most likely not quite as friable, different types of rocks and boulders. So we're getting on top of that information slowly. So we're chipping away at it. The technology, similarly, we will chip away at that. And the Artemis program, the latest moon program from NASA, is a great vehicle to fund a lot of that without investor money. It's the government R&D type funding, which will move that technology along. There's some fantastic work going on by Phil Metzger at the University of Central Florida and by Honeybee Robotics in California, a number of other places. And so we're seeing everything move slowly forward. What we need to get to is that threshold where all 5 of those things are de-risked sufficiently that folks like yourself, that the investment community can take a look at it and say, all right, in a boom time, especially sort of a mining industry financing boom time, which is what I think about it, when risk is slightly undervalued, what is going to be financeable? And one day someone will crack that nut and it'll open up. And I'm bullish that that's going to happen sometime in the next 10 years.
It was going to be my next question. It's an unfair question. I was going to ask you what sort of your 90% confidence interval is when it's going to happen. So you think that is feasible within the next 10 years? Yep,
absolutely.
Interesting. Where do you see on which of the 5 elements do you see the biggest risk?
The market. Show me customers.
Right. Where I come back to sort of, I think the government will have to sort of be the customer of last resort in the beginning.
Well,
to kickstart this.
From a personal perspective, that's one of my motivations to build Orbit Fab and make it successful, is to create that market. I'd love to put a purchase order with an asteroid mining company and buy the fuel they dig out.
So do you think that when it happens within 10 years, do you think it's going to be on the moon or on an asteroid?
Interesting one. I think that if it was just a blank landscape and I had to put money on it, I'd put money on to developing the asteroid mining side. But it's not. The moon is a capital magnet. The moon is there. Everyone sees it. They throw money at it. It's what's happening with Artemis. And so that money will move forward the geology and technology for doing things on the moon. And that may be first. Long term, I think asteroid mining is going to win out. Short term, it's difficult to say. The flip side of the moon being the capital magnet is also that the moon is a religious symbol. And so we're likely to see a lot more pressure to not strip mine the moon. Whereas the asteroids, they're like cockroaches. Nobody cares if you tread on one. So the asteroids are the cockroaches of the solar system, and it's going to be a lot easier to get permission to go and mine one. But it's going to be more difficult to get the capital together, especially that government capital.
And then if it's on the moon, do you think it's basically going to be water for the foreseeable future, or do you already see something else interesting in a reasonable time frame? I don't know, could be rare earths or helium-3 or whatever.
So firstly, there's no market for helium-3. No one wants helium-3. The Canadian government, the Canadian nuclear reactors produce tritium, which decays to helium-3, and they vent it. They just get rid of it because it's not worth collecting. It's more difficult to kick off a helium-3 reaction, which is what everybody wants, is this helium-3 fusion reaction for safer nuclear power. It's more difficult to initiate that reaction than it is to initiate a deuterium-deuterium reaction, which is already 2 orders of magnitude harder than a deuterium-tritium reaction. And we can't even get DT working for power output, let alone DD, let alone helium-3. Nuclear fusion, commercial nuclear fusion, even using deuterium and tritium, is 50 years away, has been 50 years away for the last 50 years, and I'll put it out there now, it's going to be 50 years away for the next 50 years.
That's an interesting statement because, I mean, from my knowledge of, as a financial investor, that nuclear fusion has attracted materially higher sums of investor money than anything in space.
Yeah, and if you can crack nuclear fusion, that'd be great. I'm not saying that won't be done sometime soon, perhaps in a limited way. But I invested in a nuclear fusion company, and my first startup doing instrumentation for the mining industry. At the core of our instrument was a desktop nuclear fusion reactor. Now, we were using it to generate neutrons, and we would expose the rocks to neutrons. They're highly penetrating. The rocks would then give off gamma rays, and we were able to tell what was in the rocks. So I became intimately familiar with nuclear fusion technologies, and that is hard. The ITER reactor, which is the big international effort, their 50-year schedule has a 10 or 15-year section where it basically says invent unobtainium, right? Invent a material that we don't know whether it exists or not. That's a terrible way to look at things. Some of the alternative technologies that people are working on have a bit more promise. And so when I say it's 50 years away and has been and will be 50 years away forever, I'm being a bit facetious. What I'm really pointing at is right now there is no market for helium-3. And in the foreseeable future, there will be no market for helium-3. Even if one of these reactors works, it won't be working with helium-3. Not in the near term, because that's just so much harder than existing reactions.
That's fair enough. I take your point, and I've just noted I should invite somebody to speak about fusion as well.
Oh yeah, I'd love to hear the opposing opinion to that.
However, so coming back to the moon, so you think it's just water, or is there something else attractive you can think of?
No. As I said, water and hydrocarbons is the place to start. Carbon, hydrogen, oxygen. You can do a lot with those materials. Once you have the operational capability to do that, you start to be able to look at byproducts of metals. And so even a decade ago, I wrote a paper looking at this and basically said, metals aren't the way to go. I compared it with terrestrial markets. Like what's the current price? What's the tonnage you would need to get a payback for something that might make sense for a lunar or asteroid mining sized investment? And there are only a few metals that are valuable enough. The most interesting actually is nickel. Nickel is a semi-precious metal, I guess. About 50,000 tons of nickel will net you $1 billion, as opposed to 4 or 5 tons of platinum. But the 4 or 5 tons of platinum is in such low concentrations that you need to mine similar amounts of rock to get the platinum or the nickel. And if your extraction percentages on the platinum, it's much harder to extract the platinum than it is to extract the nickel. If you get anything wrong on the platinum, you're kind of screwed. Whereas the nickel, it's in concentrations up to 20%. It's a lot more forgiving in its extraction process. Returning, of course, 50,000 tons of nickel through the atmosphere to the surface of the Earth is non-trivial and perhaps a bit harder than returning a few tons of platinum. But I don't think it's an insolvable problem. So I'm bullish on nickel being the first metal that is mined from asteroids. And the moon, there's a book out, I think, by Dennis Wingo that talks about how the moon has these nanophase particles of nickel iron, which is basically the same as M-type asteroid material, but it's in the regolith. So if you pass a magnet over, you'll pull out the native metal bits, and there's no atmosphere. They haven't oxidized and just become part of dirt. They're actually still there as nickel iron grains. And so just by dragging a magnet around, you might be able to preferentially pick up all of those parts. So it may be possible to mine that off the moon as well. But to get there, you've first got to build up an operational capability. And the first commodities, I believe, are going to be propellant. We'll work on everything else later.
That makes sense. And I'm so happy you're not one of these people who are telling these stories of like, we're going to find some asteroid that's like full of gold and we're going to bring trillions of dollars back of gold back to Earth.
No, there's a lot of hype around that, and it's all bunk.
Yeah. And for some reason, like all these calculations always seem to miss that obviously like a dramatically increased supply will have some impact on the price as well.
Yeah, and that was the point of the 2011 paper that I wrote was it's not enough to have a commodity that is valuable. If you're going to crash the global price, you've got to be bringing your $1 billion of revenue has to come from a market that's at least $10 billion annually, and that cuts down the number of metals that is viable for.
Yes, everybody needs to be mindful of the fact that we know from Star Trek, remember the currency in Star Trek? It's something like gold-plated latinum, but actually the latinum, which of course is made up, is the valuable part, and gold is just a container because it's so ubiquitous that it's not worth anything.
Yeah, I like it.
Anyway, speaking about science fiction, that's actually always how we close these interviews, and of course we've talked in futuristic terms already, and sort of like how we can get to a future that I suppose is similar to, well, not necessarily Star Trek. It's probably something more like the Expanse. But you're a fan of science fiction, and if so, what do you like?
Yeah, I read quite a bit of science fiction growing up. I blame my parents for that. My mum's a scientist, my dad's an engineer. See, right now I've been reading through Ursula Le Guin and Frederick Pohl. Yeah, those have been quite good. Earlier, Asimov and Arthur C. Clarke were always favorites.
Any of the movies or TV series you like a lot?
I'll tell you, I saw Salute 7 the other day, and if you haven't seen it, you have to get a hold of it. It's great. It's in Russian. It's not a science fiction. It's about actually Salute 7 with a bit of embellishment. Absolutely brilliantly done.
It's a documentary, or is it like a...
No, it's based on true story. I don't know if you know the story, but Salute 7 went dark, and the astronauts had to go into a powered down space station and revive it. It was quite phenomenal.
I wasn't aware. I'll definitely look that up. I mean, I must say the very few items of sort of Russian science fiction I've read or seen, I did like a lot. Like I know you had a chance to see that movie or read the novel Solaris.
Yes, I've done both. Yep.
Yeah, fantastic. Okay, cool.
Something I read recently, which I'd also highly recommend, is Daniel Suarez wrote a book, Delta V, which is about asteroid mining. Just brilliant.
Oh, yeah, I saw that on Amazon. I read through the description. That is sort of like a billionaire going off on basically one of the guys you're looking for, basically going off and financing asteroid mining. Is that it?
It was, yeah, and it was absolutely brilliant. I was riveted.
So there we go. We still need to find that billionaire, but I think sooner or later somebody will, or trillionaire.
I believe that at least one billionaire is already working on these problems.
That's good to hear. Daniel, we could go on for hours, especially about the futuristic part, but thanks so much for coming on. Best of luck with Orbit Fab as, one critical piece in the puzzle of making this future happen. And maybe we'll have you on again in a few months or a few years, and we see how the whole thing evolved.
Yeah, thanks, Raphael. It's a real pleasure. And Orbit Fab is doing well. We've got contracts signed. We just closed on some investments in the middle of this pandemic. So things are looking really good. We're out hiring. If you know any great business development people in the space industry or fantastic engineers, we're looking.
Excellent. This is based in California?
In California.
Excellent. All right, Daniel. Thanks a lot. Take care.
Thanks, Raphael. You too. Bye.
That's it for another nominal episode of the Space Business Podcast. If you like this podcast, please consider giving it a 5-star rating on your favorite podcast platform, such as iTunes. You can also follow us on Twitter at podcast_space. Also consider supporting the podcast at www.patreon.com/Space Business Podcast. If you have any feedback, including ideas for guests, and that may include yourself if you have an exciting space story to tell, or are interested in being a sponsor, or really anything else, drop us an email at spacebusinesspodcast@gmail.com. That's it. I look forward to seeing you for the next episode.